Today, I would like to talk to you about our recent work, which I'm very excited about, which we are titling LLM ROS. So LLM is large language model, and ROS is a robot operating system. This is a work from a fantastic team, including Chris Mauer, Hongzhan Yu, Yue Wan, Jonas Gonzalez, June, and myself. Right. So, as a bit of a motivation, right? We had a dream in robotics since ever, I think. And that dream is that we wanted to be able to make robots easily programmable. So since at least 1983, I found this nice paper by Professor Thomas from MIT. And then in the introduction or the argument of that paper was that we would like, one of the key characteristics is for the robot to be versatile. And to be versatile, we need to allow these robots to be programmed easily. Now, why is that important? Well, because we would like to allow robots to go beyond industrial settings. And if we would like to do that, then we would like non-expert users to be able to program those robots or instruct those robots, teach them new skills, and so forth. So this is really critical for large scale deployment because if I send the robots to my mother's house, I would like my mother to be able to instruct the robot to do something while she's not an expert robotic engineer. And I also would like her to be able to maybe teach it a new skill and so forth. So this reduces a lot the development costs because today a big chunk of the cost when it comes to robotics actually goes to the development of robot programs in order to control those robots. So I think from my point of view, we made so much progress in robotics, but we're kind of still far from achieving this goal. So let us just understand how robotics work today, more or less. So the traditional pipeline, if you will, from robotics, which a lot of robotics engineers actually follow, is the first thing an expert, a robot engineer, would actually conceptualize the desired task. So they would be, okay, that's the task I would like to solve. For example, I would like to make a coffee, let's say. Now, from that, what the robot engineer does, they actually develop a set of atomic actions. So these atomic actions are, for example, in make a cup, for instance, would be reaching to the cup, maybe, grasping the cup, placing the cup, switching the coffee machine, and so on. And then as the robot engineer thinks or the expert thinks on what other tasks they want the robot to solve, they kind of end up with a library of executable actions. So for example, now the robot could, press a button or open a door and stuff like that. So that's the first thing typically we do in robotics or robotic manufacturers do is they come and then they design these atomic actions for us and then they ship kind of the robot. Now, given a desired task and the robot itself, then the expert again comes and makes use of this library of executable actions to solve the desired task. So they would come and say, okay, I have this library of, atomic or executable actions. And then what I would try to do is, generate a behavior that solves a specific task for me. So maybe they would come and say, okay, this is an action sequence that will solve the task. Maybe they would design like a state machine, or maybe they would design kind of a behavioral tree, or even a policy, really. And then what we typically do is we deploy it on the real robot. We typically break the robot. And, there's this saying that goes, if you haven't broken your robot, then you're not a robotics engineer. And then we actually repeat. Okay, so this is kind of the traditional pipeline of how robotics more or less work. Now, today, of course, there's a lot of research to kind of remedy this pipeline, like machine learning inspired research, which I will talk a bit about later. Now, what's the problem with this pipeline, right? So if we actually look at this pipeline, we notice that in each of those three steps that I mentioned before, from conceptualizing the task to parsing and understanding the task to generating the behavior, the expert is key. So it's really all the expert. The pipeline we just talked about before, that pipeline is nothing but the expert, really. So it is the expert who actually handles this overall pipeline. So if it wasn't for the expert, this pipeline wouldn't really work. Now, why would this be a problem, right? Like, why would, having an expert in there be kind of a problem for large scale deployment of robotics? Well, first of all, the expert cannot conceptualize all the desired tasks, right? So we cannot imagine all the possible tasks we would like our robot to solve. And maybe the other question is, what are we going to do with out of distribution tasks? So I shipped you the robot, and then I designed, a set of atomic actions. Now suddenly you wanted to solve a new task which is not covered by these actions. What are you going to do? The other thing is during understanding the task, right? So what tasks does the user want to solve? Well, it is very hard to work in very general setups because you need some intuitive way for the user to be able to instruct the robot on the task they would like to solve, and you need a intuitive way for the robot to be able to maybe take that task and then map it to its actions. So it's really hard to work in general setups. But more importantly, it requires writing task-specific reward functions. So, of course, now probably you've seen the latest works by NVIDIA, which is doing Eureka, right? Which is trying to write reward functions. However, even in that type of work, they still require a sort of a fitness, right? Which is kind of analogous to a sparse reward, but that could also come from a human language. So there's much progress happening, in that area as well. And then when it comes to behavior generation, I mean, of course, because we don't know the task up front and we cannot imagine all the possible tasks and design their, atomic actions, then we can't really, manually design the behaviors we would like the robot to accomplish. And maybe more interestingly as well is, what do I do when I would like the user to provide new input, right? Like, what do I do when the user wants to teach the robot a new skill that the robot does not know? So now this pipeline, right, has been widely applied, really, and it has worked really, really well in industrial robotic scenarios. So in industry, you kind of have like a specific task you would like the robot to do, and there's typically one or more experts available. So we would be able to kind of, follow that pipeline. However, when we go to unstructured environments and tasks, this pipeline starts to fail because we don't have an expert. So if you want a robot, to cook for you, you don't really have a robot engineer, in your house that's actually going to, make the robot cook for you. If you want to explore terrains and so on, that's also similar. So our focus really is this part of the story. So we would like to be able to enable the robotic system to be deployed, much more widely than industrial systems or industrial robotics setups. And for that, we need to solve a couple of problems. So that's what we are calling robotics 2.0. So what we are trying to do is we're trying to design the next generation of robotic platforms where we are at least enabling programming of these robots from non-expert users. And luckily, with the presence of large language models, this goal might be close nowadays. Okay. So before we actually talk about the technical details, right, of how the system we designed works, let's just give it a thought a little bit, right, and try to understand what we would like to have from our embodied system. Well, the first thing, I mean, let's imagine a typical scenario. I send the robot to your kitchen, and now you're there and you want, your robot to cook for you something. Well, the first thing I need to give is ability from you to communicate and program the robot. So I want you, as a non-expert user, not a robotics engineer, to be able to specify and dictate new tasks to the robot very intuitively, right? So I would like you to specify and dictate these tasks maybe in the most common language, right, that you have, in the most common interface you have, which may be human language, right? So I would like you to be able to tell the robot, make me noodles, right? Make me pasta, make me coffee, right? And then I would like the robot to be able to understand that just from your language. I don't want you to sit down, write a reward function for what the make me coffee is. I don't want you to sit down to design a behavior for what make me coffee is, and so on. So after the robot understands the task, which is the intuitive way you spoke to the robot, and understands the task, we also would like to allow non-expert users like you to introduce new skills and atomic actions. So what do I mean by that? Imagine I ship the robot to you with, a set of skills, and now you want the robot to sweep your table, for example, right? But the robot didn't have that atomic skill because me, as a designer of the robot, I did not envision that you would want your robot to wipe the table. I mean, of course, I should have, but I didn't, let's say. So rather than you calling me again and going to the factory and telling me, look, I want the robot to wipe the table, right? Write me an atomic action for that. I want you to be able to introduce these new skills in an intuitive way, right? And these atomic actions intuitive way for the robot. So that's on your side, right? On the user side, what I would like to do is give you the ability to specify a task, and the robot understands it. And I want to give you the ability to be able to, introduce new skills. But on the other hand, I would like to also allow the robot, to understand your skill, but then I would like it to generate for you, or its skill and task, right? And I would like it to generate for you behaviors that come from you to solve your specific task. So I would like to allow the robot to generate and ground behaviors from non-experts. And the last part, which is maybe like a blue sky thing, at the end, if I am like, this is maybe the ultimate goal where we would like to reach, we don't know how to do that yet, but this is kind of the vision maybe, is we would like to allow the robot to know what it does not know. So what do I mean by that? Well, you told it, make me coffee, right? And then what happens is the robot tries to make you coffee, but then for some reason, the robot does not know how to grasp a cup, say. I want the robot to understand this deficiency. You know what? I cannot grab a cup. And then I wanted from that to spin off a simulated world to be able to learn, how to grab a cup that then transfers to the real world. Now, we cannot solve all 1, 2, 3, and 4 together in one shot because we don't want to boil the ocean. But what we're going to do in this work is we're going to tackle 1, 2, and 3. So I will give you the ability to specify the task, to introduce a new skill, and also for the robot to take those and make a plan from your task, for your task from your skills. So for that, what we have done is we defined the following system, which we call it LLM ROS, Large Language Model Robot Operating System. So on one side, we have our Pengu agent. So Pengu agent is another paper we had that is a large language model based agent, which allows you to do structured reasoning. For now, think about it as just a LLM that can solve sequential decision-making problems by talking to tools, right? By changing its intrinsic structure in order to think better. If you're interested in Pengu Agent, you can read the paper, but there's also a video on Pengu Agent on this channel, which you could go and watch. But now the idea is that we have this agent, which accepts, it has different open source. This is critical. Our experiments that I will show you later, they're based on DeepSeek Coder, which is an open source model and not GPT-4. And now what you would see is that the Pengu agent, right, will take the plans, will take the task from the user, which is allowed to be specified by language, make me coffee. We also allow this user to introduce a new skill on the robot via either imitation learning or teleoperation. And we also allow the user to give feedback to the robot by saying, hey, robot, you messed up. You should have opened your gripper here. Now, given the task and the set of actions that are available, then the Pengu agent would actually generate a plan. So that plan will be generated by the Pengu agent. It will say, first thing I want to do is that, second thing I want to do is that, and so on. Then using the middleware robot operating system ROS, which is most widely used today in the community. And I think definitely if you do robotics and you don't do ROS, you probably are not doing robotics. And then this becomes ground, like ROS will allow me to, this middleware will allow me to ground things in the real robot. Now, what is really critical in our pipeline is that we notice that large language models are typically trained on, out of robotic domain data, right? So, they're not necessarily grounded in the affordances of the robot. So that's why what we do is we allow feedback from the real world or from the user in order for the Pengu agent to replan and ground its abilities right inside the real world. So the system is made of three big components. So the first component is the Pengu agent, which you can have a look on later. But for now, just think about it as an agent, which is based on a large language model that can take, kind of an observation of the environment and will also kind of like change its intrinsic structure to allow for structured reasoning to give you actions. We have the user that will specify the task and give feedback. Then we have the middleware, which is ROS, which will allow me to kind of ground in the embodiments. And then, of course, we have the feedback to ground or to enable the grounding, let's say, of the large language model into the embodiment of the robot. So now, why ROS, you might ask, right? Well, I mean, ROS is modular and open source platform. It's very well supported in the robotics community. But also, I just found this statistics, which is saying that ROS is projected to be about $1 billion market in 2028. So definitely, kind of ROS is a way to go. Now, of course, we are not the first to attempt this, right? So there has been a lot of work in large language models and robot operating system. And if we have missed any work, we have a much more detailed work in the paper that will pop up maybe in 1 or 2 weeks. But for now, I just want to summarize a little bit. Now, the closest work to us is something called Llama-ROS, which is connecting Llama, large language model, to robot operating system. We have something called Turtle Sim Chat GPT, which allowed the control of ROS simulator using Chat GPT. And we have something called Controller GPT, which is a text that is mapped to ROS. So for example, you can tell it something like move turtle left by 2, then rotate 180 degrees and move back to 5.5. Then it will execute it here. Now, while these methods are great, the limitations, to be honest, is that mostly these are people interested, in connecting large language models to ROS. So they did these things, but they're kind of hobbyist projects and not very scalable. And the other one is that what we noticed in these is that there's no direct feedback back from ROS, to the large language model or to the agent based on the large language model for it to better plan and ground itself, right? So, that's kind of what we try to eliminate in the framework we have created. Now, of course, there has been much LLM-based robotics. This is a very brief summary of them, really. And in the paper that will pop up, you will have much more details about this. But maybe one direction was language to actions, right? So, you could actually try to map the via an LLM, a language robot starts in, and then you tell it move to, right? And it tries to map. There has been language to code, right? So put the cup in the sink, for example, then it'll create a code that will make the robot put the cup in the sink. There has been language to rewards, put the cup in the sink, but now instead of creating the code, it will actually create a reward function that you can learn a policy from. This is, for example, Eureka style of doing things. And then, of course, there has been human feedback kind of direction, like you missed, doing that and so on. Now, those methods mostly are limited in multiple ways, but many of them are not grounded in realistic robot affordances. They don't support real runtime environments because they're not really very well connected to ROS. And then typically they don't have much robotic demonstrations. The demonstrations made on the robot are relatively easy tasks, except Eureka, which I think is doing impressive, amazing stuff. And they typically are also looking at very short horizon tasks. So for example, put this here, put that there and stuff like that, but they're not really solving long horizon complex tasks. Right. And now what we hope is that our platform that we have created will allow us to do two things. One will allow us to develop more grounded robotic solutions because it's already automatically grounded in ROS. But more importantly, I'm not at all trying to propose a new state-of-the-art method. I'm just saying there's this platform, right, that will allow us to standardize the way we can have an LLM talking or an agent based on an LLM talking to a robot. And that's like a very standardized pipeline, which everybody can, write their own code in, and we can write the different methods in, and then we can compare and stuff like that. Right. So in more details, just mathematically a little bit, Um, this is our equation from the Pengu agent paper, which you can have a look at. But the idea inside Pengu agent is that the Pengu agent is trying to maximize two things. Something we call pi, which is an extrinsic function, which is the policy that you all know about in reinforcement learning, and something that is called the mu, right, which is the intrinsic function that tells us how the agent should be structured. And now all this Pengu agent tries to do is tries to find the policy pi and the mu that will maximize my total discounted reward. Now, in our case, the state will be, kind of the real world feedback state from the robot. The action will be given by the Pengu agent policy, which, you give it a prompt that has a state variable, and also it has a set of intrinsic functions, which are the structure of the agent. So this structure could say, do this atomic action followed by COT to find which other atomic action and things like that. And we also, of course, it supports RAG now, the Pengu agent. So that's another option that you can use if you had similar tasks and so forth. And then the intrinsic functions are different types of functions you can execute on the robot. So for example, you can grasp, push, you can do teleoperation or imitation learning, but also you can do reflection for replanning, right? Remember, I told you I wanted to have the feedback from Ross. So I would like to be able to do reflection to replan if I made a mistake, but also I can do fine tuning if I'm interested in, and those will be different intrinsic functions. So now at this stage, you should be excited. However, you should be worried about the reward function. Because remember my whole idea, my whole promise to you from the beginning of the talk was I want to allow non-expert users to program robotic systems, right? But if I need to write a reward function for you, then we're just not on the right track. So in other words, if for every task that you want to do, and this agent needs to do for us, we need a reward function to be written by an expert, then that's against, right, the whole goal of me not requiring experts. So instead of doing that, instead of saying, okay, the non-expert, whatever, has to write like a reward function for us, what we do is we allow feedback to come from standard human language. Now, this standard human language feedback will get rid of writing a reward function for us, and then will allow non-expert users to tell the robot, bad robot, you did bad, good robot, you did good, and maybe even give a more detailed plan saying, okay, look, you did the first two steps right, but you tried to open your gripper in the wrong place. You should have closed it first, then opened it, and so on. And then based on that, this goes back to our LLM. The LLM can fine-tune or reflect in order to give us a better plan. And this is how our pipeline works, right, all together. So we have a set of atomic actions, and then we have the agent, which can generate, behaviors that go to the real world system. Then the real world system can do feedback either from a human or from the reward if you have it, and then replanning happens. There's one component I did not speak about yet, which is this part here, imitation learning for new actions. Okay. Now, I told you I would like to achieve two things, right? Well, three things in this work. The first thing is I want to allow you to dictate the task by language. That's already done, right? Because now you have an LLM, you can instruct the robot what to do. Two, I wanted you to be able to I wanted the robot to map your task to its set of atomic actions to generate a plan. And that's already doable through the feedback, and the reflection or fine tuning. And three, I wanted you to be able to add new skills in case me as a manufacturer missed some atomic actions when I shipped the robot to you. So in order to enable that, we allow you to give two new skill ways, like to provide new skills to the robot. At this stage, we plan to extend that later. But at this stage, we allow you to do imitation learning. So the idea is that you either can do teleoperation-based imitation learning, or you can do kinesthetic teaching. So you can either move the robot, right, or actually teleoperate it. And that teleoperating it will create for us new skills. Now, once I collect the data from your teleoperation, then for now we are using something called dynamic motor primitives from the great Jan Peters to do the imitation learning. When that algorithm is done, then the LLM will store that, will write the code, right? And then we'll store that into the set of atomic actions. And now it's available if the LLM or the agent would like to use it in the next step. Okay? So now let me show you some results. So we actually have deployed this. We deployed this on the real robot, and here are some of the results. So just our experimental setup, and it's not fully complete. There are some things we could fix, of course, but we had a large language model deployment, the Pengu agent deployed in a place. We had the controller PC and the ROS environment deployed on another place. And then we had the user interacting, with the kind of like the ROS environment and the controller PC. For now, we just focused on a robotic arm setup. So we had the UR5 arm, which is a 6 degree of freedom robot arm. It has an Intel RealSense camera. And then we had a coffee machine, we had a gripper 2F85 gripper, we had a mug, we had a cabinet, we had some tools. And most importantly, and I think maybe that's the biggest limitation we have so far, but it's easy to remedy, is that we made use of April tag markers, which are these kind of markers for us to be able to handle the vision component a bit easier. So now I can localize where things are and so on. However, in the future, of course, we would need a fully flushed kind of vision language model, kind of to make the detection and so on. But for now, because we just wanted to prove this concept, we just used this simplified setup. And now we're currently working kind of to get rid of that and actually make, like a complete vision backbone, which can detect, segment, and so on. Right. So here are some of the results that I would like to mention. So here's the first result, where you have this UR5 robot, and that UR5 robot, right, will have like 2 green cubes and 1 blue cube. And now you can control what you want the robot to do from text. That's the idea, right? Like, this is my whole idea. I want you as a non-expert user to specify your task. So now you can say, okay, stack 1 green box on top of a blue box and put another green box in the sink. So, the robot's goal now, very simple task, you're going to stack 1 green on top of a blue and then put the other green in the sink. So here's the robot executing this. It will take the green, put it on the blue, right? And then it will take the other green and actually put it in the sink. All right, that works. That's easy. Now imagine I make your life a bit harder, for like the robot's life a bit harder. So I tell it, you know what? Stack 1 green box on top of a red box, put orange box in the sink, stack blue box on top of the other green box, right? Be careful, on top of the other green box, and put another red box on top of the green box. Now, please notice that when I say on top of the other green box, I mean that I want the blue box not on the same first green box, but on another one, right? That's kind of the idea. Now here, all our experiments are running with open source model, right? So this open source model, we used here DeepSeek 7 billion, right? And we really care for open source model, not GPT-4 model, because we want to be able to reproduce. I mean, this is science. You should be able to reproduce my results with an open source platform without being able, to code or to pay money, to just get access to the LLM. So that's why we just focused in this work so far on open source models. So those results are all with DeepSeek Coder, 7 billion. We tried Llama, didn't work as well. DeepSeek worked better. Now, going back to this, right? Maybe because our large language model is not as smart, as GPT-4 or something. But now what you will see here is that the robot will try to execute the task. And, we put the orange in the sink. But now the blue didn't go on the top of the other green box. It went on top of the green box. So it failed, right? So the robot failed, actually. But now, because the robot failed, I want you to be able to give it some feedback, right? Because I don't want, me as an engineer to come back and say, you know what, I'm going to write a reward function for you, right? No, I want you to be able to give it, language feedback, and then I would like the model to replan. So here's the human feedback we gave. So for example, we say here, make sure to stack the blue box on top of the second green box, right? Like, remember, it messed up here. And now I give it this a human feedback. And now what you would see is that this method is actually working. So now it will put the orange in the sink, and then it will put the blue on top of the other green box, right? On top of the other green box. So in other words, this mistake it made here from my non-expert observation, I can just tell it via feedback, hey, put on top of the second green box. And now here's like kind of a ablation study, where we use the Penguin agent, and then what we show is like, how you succeed in terms of number of boxes with and without a human feedback. So when we say planning success, this is completely LLM based, DeepSeek Coder 7 billion. And now what you could see is that, sometimes you have good success. However, when you're at 7, let's say, boxes, then the human feedback allows you, kind of to succeed much more. Okay. So now all this was easy, right? But I mean, I was arguing, oh, the current limitation of the other papers is that, they just do like short horizon tasks. So what we wanted to do, right, is we wanted to be able to do a bit more complex things than that, right? So we wanted to, allow the robot, right, to be able to learn from you, learn from your skills, something new, all right, and then be able to deploy that into its atomic action library. So that's a new skill that has been learned. And we wanted that to be deployed into its atomic action library, and then used when I ask it via a prompt to do something else. So now imagine you're a non-expert user. I ship this robot for you, and now you want your robot to make you pasta or noodles or something, right? Well, for you to be able to do that, you need to give it some skills. Maybe I did not code them, as a robotic engineer. So now, to allow you to do that, I will allow two forms, either kinesthetic teaching. So like here you see Yiwei is actually teaching the robot, how to grate an onion. Or we also have another set of experiments with teleoperation, which you will see in the paper. But here is Yiwei trying, to kind of teach the robot how to do, this grating an onion. And then, the robot would do something called dynamic motor primitives. And then the robot would be able to kind of to learn, how to actually grate the onion, right? So that's kind of what is going on here. But you can also teach it many other skills, like, for example, a pouring skill. So here's Yiwei teaching it to pour something, right? And then again, with dynamic motor primitives, kind of the robot, right, is capable of learning, how to be able to do that. Now, you might say, why did we use dynamic motor primitives? Well, there are two reasons. One, dynamic motor primitives, which is an algorithm from Jan Peters, is extremely data efficient. So in fact, the results you see here are coming from one demonstration of the human. One. I'm not saying 100, I'm not saying 100,000, I'm saying one. So one demonstration of the user, we got these results. Of course, there needs to be improvements. If you want to go fully flushed vision, you need a bit more than that. If you want to generalize much better, you need a bit more than that. But these are things are currently kind of working on. However, we believe, dynamic motor primitives are a way to go, and maybe we can improve them and scale them. And I think Professor Peters has already done some work in that direction. Right. So now with this, I can allow you to update your action library, while doing imitation learning, right? So I can actually allow you to do that. So now what happens, right? So now I would like to show you that with this, you are able to solve, a set of long horizon tasks. So now I want to utilize the learned actions, to solve a long horizon task. So Yiwei, let's say he's a non-expert user, and he came and said, I want to make noodles, but my robot does not know how to make noodles. So the first thing he did is he came and taught some skills that are needed to make robots via kinesthetic teaching. The robot took this and added them to its atomic action library via an LLM. Then after that's done, Yiwei comes and says, hey, look, can you make me noodles? It starts by grating an onion with me, right? So you're going to grate an onion with me. So you see there's a collaborative task. Then you're going to pour sauce. Then you're going to stir with the spoon, toss the wok, and finally add seasoning. Make sure to dispose any utensils in the sink. So that's supposed to be the sink. Now, please notice, right? What is really important here is that the robot is not going to follow, the step-by-step plan as I've written it in text, because it will do replanning. Let me explain why. Because if you read this, then you would know that the first thing you want to do is you want to grate an onion with Yiwei, right? Two, you want to just get rid of that onion, because I say at the end, make sure to dispose all the utensils in the sink. Then you're going to pour the sauce. Then you're going to, get rid of that. Then you're going to stir with the spoon, then get rid of the spoon, and so on. So it's not just one-to-one following exactly my language. This is a very generic LLM that's actually taking this and mapping it to the atomic actions that have been learned or available, learned by kinesthetic teaching or available. And then there's the feedback system that will allow me to do better. So this is the demonstration here. So that's the way. First thing the robot does is creates the onion, and then it throws the onion in the sink. Then the second thing it does, it will kind of pour the soup, right? So that's the idea. Then it will throw the soup can or the cup in this case in the sink. Then it will stir, the soup. After it stirs the soup and gets rid of the spoon, then it's now going to toss the wok, right? So now, as you see here, that's kind of the tossing, which also has been taught kinesthetically. And then, of course, it made a mistake, so we had to make a minor correction here. So we're working to make that a bit more stable. And then at the end, kind of like added the seasoning finally. So this is one long horizon task that we were able to solve with the thing that I mentioned. And another long horizon task, which is also important to mention, is the task which is, can you make me coffee? Because what you're going to see now is the LLM will generate a long horizon sequence. The prompt will require a recipe in this case and COT examples. And then we're going to demonstrate a very long horizon task of making a coffee, as you will see next. And this is, I think, maybe not the first to say, but it's relatively new, that just from the prompt of make me coffee, and the recipe and some few short COTs, the robot could actually do all that automatically. So here we enabled here we enabled some also like text to speech to text. So here you see Hongzhan Hongzhan just says, "Can you make me coffee?" But that's not that difficult, so to say. And now what you would see here is now the whole robot is acting based on the Pengu agent. So the first action it decides, grab the cup. The second action it decides, put the cup in the coffee machine. The third action it will decide is, I think, open the coffee machine, right? That's 3. And then the fourth action it will decide on is open the cabinet, I believe, because that's where the coffee beans are supposed to be. So now here you would see it opening the cabinet. Please notice that opening the cabinet is a complex task because the robot cannot reach. So it opens the cabinet, then it pushes it forward. Then the fifth action is going to be take, the coffee beans from the cabinet. That's the fifth one. Then it's going to take the spoon, sixth action. Then it's going to decide, take for me some coffee beans, right? And take for me some coffee beans. That's, I think, seventh action or so. Then it'll decide to put it in the coffee machine, eighth action or so. Get rid of the utensil, ninth action or so. Then it's going to close the coffee machine. And then it's going to decide to clean. I wouldn't have done that, but that's what the LLM decided. I'm going to clean before I press the button, to make coffee. And then here it's going to close the cabinet again. And now it's going to, press the cup, right, of the coffee machine. And that it made coffee for us. So please notice this is like I think maybe over like 15 or something, a sequence of actions or something like this. Is a seriously long horizon task. So now this long horizon task can also be achieved with this. So the next things we want to do is, I'm not saying this is done, but we have to, for example, look into how we can handle changes in the environment. Like if, for example, the goal object moved, then what happens? How can we deal with that? That's what we're currently working on. And we want to show that the robot can recover from problems by human feedback, but in more complex tasks than we just showed. And then we want to also see that if it can learn from mistake. And now maybe one cool experiment we're going to do is that we're going to do remote supervisory control. So we have an operator sitting somewhere, we have a robot sitting somewhere else, and there's communication across the internet, maybe via 5G or something. And then the tasks could be like offshore tasks, maybe oil inspection or maintenance. And then, we require like situational awareness. But directly teleoperation is difficult because of network latency. So we aim to demonstrate that this framework is intuitive to do supervisory control, and we also aim to show that we reduce the burden on the operator. Now we aren't done. This is just the first step. We still need to introduce reinforcement learning very well. We still need to do domain randomization, and we still need to do vision language models. So this is the start, this is good, but we need to be able to handle vision better than we currently do because we use, these April tags. We want to be able to do that with the vision language model. We want to test across multiple robotic platforms. I mean, this worked well across the UR5, but now we are planning to test it across a wider range of platforms. And we are trying and working to kind of like be able to share our code, hopefully, and then we need to be able to kind of identify the missing skills, as I told you, this ultimate dream, to bridge this sim to real gap. But for now, what we have is the system, and this system is capable of solving relatively long horizon tasks. As I showed you, it will allow you for three things. One is it will allow you as a human to specify the task for it via language. It will also allow you to introduce new skills via kinesthetic teaching or imitation learning. And then it allows you for grounding in robot affordances via feedback. So that's all I wanted to talk about this today. I really hope you enjoyed the talk. If you did, please make sure to like, subscribe, and share. And if you have any ideas or questions, please write me in the comments below. I'll be really excited to answer them. So see you next time. Thank you.